Bismillahirrahmanirrahim. Assalamualaikum and very good evening to all of you. Welcome back to our class, the BAA 2213, the Reinforced Concrete Design 1. For today's class, I will focus on the example 5.2 from the module book, which is the determination of slenderness of the column. Okay, this column is based on the key plan of example 5.1. And then we have to design the column located here at B2. Okay, column located at B2. Here for more exact, so I can sketch. Okay, sorry. Okay, this one. Okay, so you have to design the column located here at B2. Okay, where we have for this column we have 4 number of beam, but the beam size is different. Okay, this is beam 1, 2, 3, and 4, but the beam size is different. 250 times 500 and 250 times 450. Okay, so for this example, you have to determine either the column is slender or not. So this one, 3.6 meter here is the total height from the ground floor to the level. Okay, as shown in the figure 5.1. Can you see the ground floor to top level is 3.8 meters. Okay, here is it. Okay, and then this is the beam from B1 to 2. Okay, 1 to 2. This is the length is this one. This one should be 1 to 3. 2 to 3. Okay, 2 to 3, and then this is the 1 to 2 is 4 meter, and then the size is along grid line B. Okay, 250 times 450. Okay, this one. Please take a look on the depth of beam because it will contribute to different effective height. Okay, so this one, and then for this one, this beam is from 2A to B. Okay, the section is 250 times 500 and the length is 5.5 meter. And another one is here. Okay, also similar size and similar length. This beam is from B to C. Okay, you can refer to this layout. Okay, so you know now the position of the beam. Okay, let's say it's better for us to, okay, let me just screenshot and then do it in the Word. Okay, so this one. If you have questions, so you can stop me. Okay, so this is the beam number. Okay, so I can draw. Okay, this is beam. Let's say we name the beam as A. This is beam A. And then this is B. 5/4. Okay, sorry, A is here. This is A. And then this one is B. Okay, I hope you can imagine. And then this one is C and this is D. Okay, so this beam is C and this one is D. Okay, this is the first floor level. Okay, and this is the strength of materials. And then this is the N. Okay, the N is the actual force obtained, okay, from up to here. Okay, this is because we want to design the column. The column we want to determine either this column is this one. The column here is slender or short. So determine it up to here. So the 888.91 is the value, 888.91. is, you can refer from, okay, here is from this calculation of example 5.1. Okay, we will take a look later by next week. Okay, so this is the value. Okay. Okay. It exclude the ground level. Okay, the loading from this slab here is exclude. Okay, only considered from roof and from the first level. Okay, as the actual load. Okay, and then the value of bending moment here is, okay, this one. This is mz and my. So mz is, we have at the bottom is 9.99, and at the top, okay, here, let's say here, okay, I hope you can see the word file. Okay, let me enlarge. Okay, this one. Okay, but okay. So this one is, this is the at the top, and then this is at the bottom. Okay, the top moment here is, okay, m top, and this is m at the bottom. Okay, and then so this is the 9.99 from this calculation. Okay, from these calculations, so we just extract this from this figure. We extract this one. Okay, because this is the ground floor level, and then this is the first floor level, and this one is for the roof level. So we want to determine either this column is slender or not, so we consider this part only. Okay, so this is the mzz, and then this one is for the mzy. We consider only this part. Okay, 10.91 at the top and 8.32 at the bottom. So we got, okay, so this is the bending moment we have to consider. Okay, from the elevation plan view, we must detect first where is the z and y axis. Okay, I cannot see it here, but it's okay. We can detect from the equation later. mz is come from, okay, this one. Okay, alhamdulillah, this is y, this is y. Okay, so this is my, mz. Okay, mz, this is 300 and this is 250. So this shall be, okay, this is z. Okay, sorry, okay, this one is z to z. So the column here is z is here. This is 300. This one is, this side is 300, and this side is 250. So okay, so first for the beam 1 2 3, sorry, okay, okay, so this one, okay, I hope you can imagine. Okay, this is the dimension. Okay, beam 1 2 3 means here. Okay, beam 1 2 3, the this here, beam b stroke 1 up to 3. So this is the beam. Okay, this is the beam. The dimension is 250 times 450. Okay, and then the length from 1 to 2, the length is 4 meter, and from 2 to 3, the length is 5 meter, okay, as shown here. And then beam at grid line 2 stroke C. Here, this is the beam C and beam D. Okay, the length is 5 meter, 5.5 meter, and the dimension for both beams is 250 times 500 millimeter. And then the column is B times H is 250 times 300. So, okay, I hope you can imagine for this beam, let's say we, okay, how to A and B, okay. So this one, so means here, this is the side of, okay, this is the column, okay, let me enlarge. So if I enlarge, so this column is like this one, okay, this is 300 and this one is 250. Okay, you can correct me if I am wrong. It's okay. So this one, so the LZ is the effective length, okay, effective length of Z directions, okay, of the Z axis. So this one 550, okay, this one for 550. So let's say you have a beam here, okay, we must look from this, okay, this is the beam, and okay, this is a beam at the first floor, and this is the beam at the ground beam, and then this is the column. This is the column effective length. I mean the clear length. Okay, the clear length here. Okay, let's say so. It's from here to here is, what is the length? 3,800 millimeter. Okay, so this is here is 300. Okay, here the column is 300 here, and then what is the beam, the depth of the beam? The depth of the beam is 550 because this beam is here, beam A and beam B. Okay, along the Z axis. Okay, this is the Z axis. So this is beam A and this is beam B. So we want to know the clear length here is very simple. The LZ is equal to 3,800 minus the depth of the beam for 50, so equal to 3350 mm. Okay, and then for this side, okay, this is for this side. So from we cut here. Okay, we cut here. Let's see. Then we have beam. Okay, this is beam, and then the beam is from C and D. Okay, this is the roof, and this one, this one is first, and this one is ground, and then this is the column. Okay, the column. However, the side, the here is this one. This one is the from here. Yeah, this one is 250. Okay, because this is C and this is beam C and this is beam D, and then the depth is the size is 250 times 500 mm, and then from top to top is similar, which is 3,800 mm. So the value of L Okay, this is the axis. Ly is equal to 3,800 minus 500 equal to 3,300 millimeter, like as shown in these calculations. Okay, so I hope you can imagine and you can understand, okay, why the value, how to get to differentiate the LZ and Ly. Okay, and then the stiffness is okay. This one, this the for the stiffness is the K is equal. Okay, the stiffness. Astaghfirullah. Okay, K is equal to I over L, where I is equal to, okay, BH the power of 3 divided by 12. Okay, so that's why for the Z, okay, for the Z directions we have here, Z directions. So that's why I need two. I need more than one file. Okay, so you can refer here. It's okay. So this one Z direction, Z is 300. So you multiply to the power of 3. But so the Z axis, okay, rotate about Z axis. So the KC is equal to 250. 250 is the B. H is 300. So like this one. So this calculation is simple. So you must know this is B, means this is B, this is H. Okay, so it's equal to 250 times 300 to the power of 3. Okay, divide by 12 actually, and then divide by the LZ. LZ is equal to this one, 335. Divide by 33550 is equal to this one, divide by 12. So times 1 over 3350. So similar to the KCY. So you got this value, and then you have to calculate the stiffness of beam. Okay, so also similar. B is this one. This is the H. So you multiply. Make sure you enter the right L. Okay, because the L is different L. So between KB ZY Z2. So this one is beam number. It's okay. I will give you the word file later. Okay, this is beam A. This one is beam B, and this one is beam C and beam D. So the next step is to calculate this one. Okay, K Z axis. So you just okay, for the Z axis you just this one 1.1. So you use the corresponding value. This one from Z axis K2. Just use this. Okay, K is equal to K column divided by 2. Okay, K beam. Okay, K. This one Z axis. So column to the Z axis is which column? Which column? Which beam? Of this beam. Okay, beam A and beam B. So beam A and beam B, you refer back to here. This is beam A, as I mentioned before. This is beam A, and this one is beam B. So 4.75 plus 3.0. So okay, this one, and then for use the similar. Okay, if the value is more than 0.1, so you use 0.1 as the K1 and K2 at the top and bottom. So for the y-axis, you just use the value. Okay, this is the KC for y-axis 1.18. So you put it in this calculation here, and then for the y value, you use the beam. Okay, y value is this direction. So use beam C and beam D. So the value is 4.74 here. This one 4.74 to the power of times 10 to the power of 5. Similar value for both. So you just use the if the this one is greater or lower 0.06. Can you use your calculator to calculate this one? 0.06 shall be let's do it together. 1.18 divided by 2 times 4.74 plus 4.74. So the value is, where's the value shall be? 1.18. So equal to 1.18 divided by 2 times 4.74. 1.18. Sorry, 4.74 plus 4.74 times 2. So 18.96. Okay. Divided by 18.96, 0.06. 106. This one is smaller, should be smaller. So you just use 0.06. You should be you should use 0.06. So you use 0.06 and then you use here also 0.06. Also here, can you check for me? I think this one also 1.68 divided by 2 times 2 4.75 plus 3.8 equal to 1.68 divided by 4.75 plus 3.8 times 2, 17. 1. So 1.68 divided by this one. Okay, 0. This one. Okay, this one is round up. Okay, actually 0.098. So round up to 0.1. So you can use 0.1 here. So you must for the y-axis. Okay, maybe you have to recheck this value. Either this one, the K1, K2 is right or not. I think okay, because should be similar. Should be similar. It's okay. Let's do it together. Okay, so K1 plus 1 plus 1 plus K1 over 0.45 plus K1. Okay, if the K1 is for the Z, for the Z axis, is it 1.18 or not? Okay, so please check this one. So 1 plus 0.1 divided by 0.45 plus 0.1. Can you get the answer? Similar answer?
Yes.
Yes. Okay, good. So 0.1 divided by 0.55. Okay, and then plus 1. 1.18. Okay, this one, the Z axis. Okay, so this one, the answer is 1977 is right. Okay, but what if the K1 is for the L0Y? I don't think the answer is 1.18 because this is 0.06, kan? 0.06 and then 0.06. 0.46 plus 0.06. Okay, 0.06 plus 0.06. Okay, 0.41. Sorry, yeah, I just use ordinary calculator. So, okay, what is the answer now? Divide by 0.51. 1.1, 1.12, right? This one should be 1.12.
1.112. Oh, yes.
1.12. So you have to check. Okay, this one 1.12. So 1.12 the value is, so this one 87. Okay, this one, okay, this is I. Okay, the radius of gyration is I divided by A to the power of 0.5. Okay, so here, okay, I is equal to the Z. Okay, I 5.53. So, okay, I over A. Okay, to the power of this one. Okay, this is the radius of gyrations. Okay, so the A is simple. A is straightforward from, okay, A is 250 times 300. So can you check for me? Is it right, the answer? 250 times 300. Okay, 75,000. Okay, like this one. This is the value of A. So the I is equal to BH to the power of 3 over 12. So B 250 times 300 to the power of 3 divided by 12. Is it similar to the answer?
Yes, similar.
Similar, similar. Okay, 5.6. 3 times 10. Okay, how about this one? Is it also similar? And, okay, so 3.19. Okay, because this one, the I here is equal to 300 times 250 to the power of 3, because the different directions. Okay, so different value. So 3.91 to the time. Okay, so this one is okay. So I have to, okay, class, welcome back to our class. Okay, so this one, okay, can somebody tell me what is the value of LOY here? If the value here is not 1.18, this value is 1.12 actually. So what is the value here? Can somebody use your calculator for me? What is the value of LOY?
1896.
Okay, so 18, 18, oh,
1896.
Okay.
1896 mm.
Okay, thank you. Okay, so this one, so you just, okay, you just determine this the value of here, this the radius of gyrations I over A. Okay, and then Isaac is equal to 87. So this one is 87. You bring it here, and then IY is 72, and then so please, okay, you just the value is this one 1896. Okay, so what is the new value here for slenderness ratio. This one, 27 is shall be. This one is okay, 22.7. Okay, and what is the value here? Okay, 26.3. Okay, thank you. So, okay, this is the slenderness ratio. So you have to compare the slenderness ratio to its limit. So you can use this equation. Okay, the limit is equal to 20 ABC divided by n. Okay, set n. So this is you just if this value and this value is not known, so you can just use the A is equal to 0.7, B equal to 1.1. Okay, as in the note here. Okay, this one. Okay, this one. Clause. Okay, this from this clause in Eurocode. Okay, equation 5.13 in Eurocode. So you can use 0.7 for A, 1.1 for B. And if the C is not known, you can use 0.7 also. This one, but since we are already okay, so this one the value of A is equal to 0.7, value of B is equal to 1.1. So the value of C actually we can use 0.7 if unknown. But since we already is from example 5.1, we already know the value of moment at the top and at the bottom. So you can calculate by using this equation. C is equal to 1.7 minus Rm, where Rm is equal to MO1 divided by MO2. MO1 is at the bottom, right? Sorry. So we wait to check. So this one, okay. Yes, MO1 is at the bottom here, this one. Okay, so 9.99. Okay, sorry here. Better use this one. Larger view. Okay, oh, tak boleh, tak nampak. Okay, sorry. Okay, so this one. Okay, 9.9. Okay, you refer to here. Okay, so this is MO1, MO2. This is also MO1, this is also MO2. But this is for Z and this is for Y. Okay, so 9.99 divided by 14.17 and 8.32 divided by 10.91. Okay, so this one, okay, and then here 0.17, you bring it here, you get the C, Z, and then you got the this one is CY actually, yeah, CY. Okay, from this value. Okay, this is the bending moment. Okay, MO1 divided by MO2. Okay, and then you for both axes you use the corresponding value of C. Okay, so this one this is the limit. Okay, this is the limit. Okay, this is the A and this is the B. This is the A, B, and C, and then this is A, B, and C. Okay. Okay, n, and the value of n here. Okay, what is the value of n? This is the n, the 0.84. How to get the 0.84 is by using this equation. Okay, AC is equal to this one. AC is equal to the size of the column. Okay, which is 250 times 300, and then FCD is equal to this. Just simply use this equation. 0.85 FCK is the strength of concrete. YC is the partial safety factor. Okay, so you just sub in the value here. So and then this is this one 888.91 times to the 10 to the power of 3, which is the n, is obtained from example of Okay, from this one. Okay, which is from example 5.1. Okay, you can go through and you can recheck either the value is correct or not. Okay, and then you determine. Okay, this is the limit. Okay, the limit here is for the z-axis. The limit is here. Okay, 16.6, and for y-axis the limit is 15.8. So it's both directions over the limit. So column is slender about z and y axis because it's over the limit. Okay, but this step is involving the long calculations where you must know the stiffness. Okay, the stiffness stiffness is useful to determine the effective length, and then you need to know the radius of gyration before you can know the slenderness ratio, and then you check compare with the limit. However, you are allowed to use the simplified method. Okay, from this table you can just use the coefficient. Okay, for your project I think you better use this method. Okay, for your project just skip this one. Okay, but you must know. Okay, you must know this one. You can use both methods. Okay, you can use a simplified method, or you can use this one, the longer one. Okay, where for this method you need to know the stiffness of column and the beam. You have to determine. But okay, just follow this. You can use this example as reference. But however, you have to derive from before you start your design. You have to derive your bending moment, y or z, both. Okay, M01 y, M02 y, M01 z, and M02 z. Okay, and then you have to know the value of n. Okay, the axial force. This one is compulsory for design, but to check the slenderness you can use simplified method. Where to use the simplified method, you must know the effective length is equal to factor multiply by the clear height. Okay, this is the clear height as we calculated before. This is the LZ, and this is the LY. Okay, so this is the factor. The factor you can obtain from this table. Okay. Okay, the conditions. Okay. Okay, from this table. So this is the conditions. Conditions 1, the end of the column is connected monolithically to beams on either sides, which are at least as deep as the overall dimension of the column in the plane considered. Where the column is connected to a foundation structure, this should be a form of specifically designed to carry moment. Okay, if the depth of deep, okay, deep as the over dimension, at least as deep as the overall dimension of the column. Okay, so the depth of the beam shall be at least similar to the depth of the column. So if the depth of the beam is shallower, okay, then the condition is 2. Okay, for this one, while not specifically designed, okay, this is rotation of the column, they will provide some nominal restraint. This is unclear. So for your project, and for most cases, it's okay, the end condition at the top, and this is the end condition at the bottom. So since by referring to this example, okay, at the top end condition is 1. Okay, because the beam is both sides. Here, this is the HC, the depth of the column is 450. However, if the beam, let's say the beam here is 250, very small beam, 150 times 250. So the beam here is 250. This is lesser than 300, lesser than the side of the column. So the condition here is not 1 anymore. The condition here is here 2. Okay, the keyword is shallower here. Okay, the condition is 2, so the coefficient will be differ. So but since the top and bottom is the beam at the top and beam at the bottom, okay, I must show you this one. Okay, this one. Okay, the beam here, okay, 450. Let's say, okay, this is must be 450 also. Okay, you must refer to the layout. Refer to the layout in, okay, beam in grid line. Okay, this one, okay, 450 also. So it's greater than 300. So this is end condition is 1, and this is also 1. At the top and bottom, the end condition is 1. So since the end condition is 1, so you just select, simply select here. This is at bottom, the end condition is 1, and at the top, the condition also 1. So the coefficient is 0.75. Okay. So you can just use the condition is, sorry, this one. Okay, so this one 0.75 times the clear length. So this is the effective length. Okay, effective length is for Z direction, and this is for Y directions. So you can simply use, okay, just use this one. You bring it to the equations to check the slenderness ratio. Divide by 87. 87 you must calculate. However, you must calculate the value, the radius of gyrations here. Okay, this one you cannot escape. This one, okay, this step you cannot escape. You must calculate. So you got, okay, the slenderness ratio, and then you also must calculate this one, the limit. You also cannot escape. You cannot excuse this one, but this one is very, very simple, since you just can use the value of A, B, and C. If you know the bending moment, you can calculate the value of C equal to 1.7 minus Rm. So Rm is equal to MO1 divided by MO2. Okay. Bottom, okay, this one, the bottom divided by top. Okay, so you can compare to the limit. So it's still greater than the limit. So both direction is slender columns. Okay, so in our next class, we will discuss about the example 5.3, design of non-slender column bent about the major axis. Okay, this is the situation given, and we can design. I think we have to, we have to refer to the design chart. Okay, I will show you on how to use the design chart later. So make sure you are available for our next class. Okay, this is a very simple. Okay, and then 5.4 we can do also, and 5.5 is about the biaxial bending. Okay, this is quite complicated, but it's okay. I think you can refer to the video and then for your revision. Okay, please you must be able to determine either the column is slender or not. Okay, and for your project you can use this method. Okay, class, any question? If no questions, so I think all the best. See you in next video.